So, welcome everybody to today's colloquium. So it's a pleasure for me to introduce today Christopher Monroe. He is a distinguished professor at the Duke University and the director of the Duke Quantum Center at Duke University. He's one of the pioneers in trapped ion quantum computation. And he's one of the co-founders of the company IonQ that is actually meant to, or is working on bringing trapped ion quantum computers to the market and to actually commercialize such systems. And he will give today an overview of quantum computing with trapped atomic ions. And for me, it's a pleasure to actually give you now the word to you, Chris. It's up to you now to start.
Okay, thank you, Marcus. I appreciate the introduction. Well, thank you all for attending what will maybe be one of the last virtual lectures you go to, we hope. At the same time, I'm sorry that I couldn't be there in person. Much rather deliver a live lecture. However, I'm happy to be with you this afternoon, and I hope you have questions. It might be hard to interrupt during the talk, but if you can do that, go ahead, and we'll see if I can stop. But certainly there will be time at the end. So I presume most of you have heard of the topic of quantum computing in the field of quantum information science. But given this is a fairly general talk, I will spend some time at very high level defining terms and hopefully conveying the sense of excitement in the field, partly because I know I'm recorded and I probably shouldn't be saying this too loudly, but we don't know exactly how these things will be used in the future, but there are many hints and it's quite promising. So there's obviously lots of investment from governments, but also, as Marcus hinted, private money, private investments through industry are playing a big role over the last 5 or 6 years. So my main job is at Duke University. I actually recently moved there, but we're establishing a quantum center, a quantum computing center. I'll talk a little bit about that, but I'll also touch on a little bit of what's happening at the company IonQ, which was a startup 5 years ago, and now it's a big, actually fairly big public company. I want to tell you a little bit about what's going on there. Okay, so at a very high level, I look at the field of quantum computing as being a confluence of, you might argue, are the two maybe most important developments in the 20th century, and that is computing, information, and quantum physics. And I think up until the last few decades, quantum physics has been a little bit esoteric, at least in the general public. There are many weird and strange aspects of quantum physics that you don't really need to understand to get the basic workings of a transistor or a laser. You just don't have to think about quantum measurement and some of the philosophical underpinnings. But in quantum computing, you really have to dive in and deal with the absolute most strange features. And so it's a very nice time for physicists because we take those as second nature. We use quantum mechanics. We're at least comfortable with the prescriptions of quantum physics. And now it looks like that will be very useful for future technology. But information theory, physicists don't tend to have as much of an appreciation for information theory. I certainly didn't. And as is one of the great features of this field, we're all students and we have to learn things that we probably should have known. Well, the theory of information was largely codified in the mid-20th century by Claude Shannon. And he quantified the term the bit, the binary digit, the fundamental unit of information. A heads or a tail if it's a coin. Any two-level system can behave as a bit, as you know. And Alan Turing in the United Kingdom was a theorist who codified the general theory of computing, what it means to compute using bits And this abstract picture here is called a Turing machine. And nobody has really built a Turing machine that looks like this. It involves a bunch of memory, a bunch of two-level systems that can be flipped and store their values, and they move in front of a head, or this read-write device that has also its own memory, but it can do computations. It can do, depending on its internal memory, it can flip the bit and the memory and so forth. So this turns out to model every type of computer we have, even though they don't look like this physically. And I think the common theme between the theories of these two men is that the concept of computing and the concept of information is totally independent of hardware. And that was a key understanding in the 20th century. And in a sense, it freed us physicists and engineers to look for systems that could represent bits and make computers out of those systems. And of course, we have beautiful pictures from the 20th century. The first vacuum tube, the first large scale digital computers were built out of vacuum tubes. And these are three examples from the US, the United Kingdom, and the Soviet Union in the mid 20th century. And as always, the Soviet Union was a little bit behind. The components that go into these computers were, of course, vacuum tubes, and they were mass produced, but they were pretty unreliable. I mean, there's a lot of physics inside of a vacuum tube, of course, but they had to maintain a low pressure, and they weren't very reliable. I think these machines had many thousands of vacuum tubes, and there was even a full-time position for somebody to keep changing the vacuum tubes to make sure they were working. So in the spirit of technology, searches for technology that can store bits, as physicists, we all know this beautiful picture of the first solid state transistor from Bell Labs here in the US in 1947. And this is a chunk of germanium, this dark kind of crystal on the bottom. And this gate here is it's a piece of glass with a gold foil on the tip of that triangular shape, and all of the action happens right here at this junction. And so when a current goes through this gold, it can control a much larger current from the source and the drain over here. So this is a current dependent switch. So this also, by wiring a few of these together, you can make a bit, and you can make a memory. And of course, this underlies all of the computers we use now. And it turns out we didn't use germanium. We went over to silicon. And it's interesting looking at that history. And I'm talking about this classical computer history for a reason, because a lot of it is being repeated in the quest for building quantum computers. And the first example is that it's the transistor action started in germanium. And you can argue which semiconductor is the best, but silicon is really what we use now. And it's not because it has better physical properties at the fundamental levels. It's because techniques were invented to scale it up like crazy. And that's called VLSI, very large scale integration. And this device here is not very reliable. In fact, I would say it's probably less reliable than a vacuum tube, the first transistor here. But by understanding how to build them en masse and eventually pack billions of them on a single chip in a clean environment, they can be made incredibly reliable, of course, and that's what we have now. So the growth of silicon semiconductor technology for computers is what underlies what we call Moore's law, which is an empirical law that we just saw from industry. They were able to shrink the size of transistors almost a factor of 10 every decade, or a factor of 2 every couple of years. And so this is a plot of Moore's law. The number of transistors on a single computer chip, a CPU, a processor, over time, over the last several decades, relative to 1978. So it's scaled to 1978. And you can see this exponential growth right here. You can also see signs that over the last 10 or 20 years, it's starting to taper off. And this is simply because the transistors are getting so small that they're actually consuming more power per unit area. They're getting more expensive, and so it is slowing down a little bit. They're also approaching the size of large molecules. These transistors are now several nanometers on a side, so you're starting to actually come across limits due to the quantum, the granularity of matter. Okay, so I'm not here to say that quantum computing will allow us to continue this amazing growth on Moore's law. Some people say that. I think that's a little bit overhyped. However, the fact that it is tapering does lead us to wonder, is there a new model of computing out there? So I put Moore's law up there because Richard Feynman, I think this is well before Moore's law, at a physics conference in 1959. He was, I think, struck by this picture here of the solid state transistor. And I think he recognized that because it's solid state, the physics allows it to be shrunk to very small dimensions. And he has this wonderful paragraph in this speech. The speech was called "There's Plenty of Room at the Bottom," meaning that you should be able to really shrink these things down. And he imagined that when we get transistors down to the atomic scale, where we have circuits with just a few atoms, he foresaw that there would be completely new opportunities for design. And the reason, it's a physics reason, because at that level of simplicity in matter, when you have very few degrees of freedom, the laws of physics are basically different. And whenever you change the fundamental laws underlying something, it's just going to be new opportunities. And of course, those laws are quantum mechanics. And this is sort of the background I look at it in quantum computing. In 1959, the term quantum computer wasn't there. Nobody knew what that opportunity would be. But I think now it's very clear that quantum computers are this opportunity. So let me, for this audience, I don't need to give you a quantum primer, but I will explain this opportunity in terms of bits. Now, quantum mechanics is not typically taught with an information theory type background. And I think that's changing. I tend to teach it from that perspective. And I think when you extend the concept of a bit to a quantum bit, it's a very natural thing, because a quantum bit is simply a two-level system, a quantum two-level system. So we write it in this way. A single quantum bit, it can be expressed as a superposition of two values, 0 and 1, whatever they are. They could be energy levels of this single electron. That's one electron in two places, if you want. Or it could be the position of an atom. It could be the current in a superconductor. There are many realizations. But of course, the main point is that the superposition has continuous variables, complex variables, that describe the weights of how much 0 and 1 there are. And to me, this is actually not so strange, the idea of a wave. And there's a wave equation that underlies how alpha and beta evolve. The Schrodinger wave equation, we all know. But the most strange part, at least to me, in quantum is the measurement. And that is, we don't experience superpositions in every day, so we have to invent sort of a fix to the rules that allow us to have definite states when we measure. So the standard approach, sometimes called the Copenhagen interpretation, there are many other interpretations. They all give the same answers in all conceivable experiments. So to me, they're not really remarkable scientifically. But so the Copenhagen interpretation has flaws that Einstein very, very much pointed out, but this is how most physicists think of quantum. And that is, the quantum superposition, when you measure it, it collapses. The state collapses to one or the other state. So the and becomes an or. And we have to use the language of probabilities to understand what's going on. And not surprisingly, the probabilities are related to these weightings, these amplitudes, alpha and beta. It's the modulo squared. And this allows the wave equation to, anyway. So the Schrodinger wave equation and probabilities being the mod squared is basically the Copenhagen interpretation. Okay, so that's a single quantum bit. It's sort of pedestrian. We can store superpositions and measure them. There's nothing new there. But when we put lots of quantum bits together, things get very interesting. Now, a very general superposition of multiple quantum bits can carry something called entanglement, which again, up until probably the 70s or 1980s, was sort of a curiosity. It comes along with superposition. And the idea here is that this is the simplest entangled state you can write. It has two quantum bits. Sometimes we call them qubits. when you have these 2 qubits prepared, for instance, in this particular state, it looks fairly innocent. This should be allowed, and alpha and beta follow a Schrodinger equation. But when you measure either quantum bit, you know for sure that the other quantum bit is in the same state. And that's kind of interesting. It seems like there's a correlation here, a perfect correlation, even though the individual qubits are, in a sense, in both states. So it's sort of like randomness at the individual scale, but not so much randomness when you have a bigger system. And that, that sub-additivity of entropy is something weird. Usually the entropy of something grows when you add to it. So quantum entanglement is a counterexample of that. And when you think about information entropy, the entire law of information, the theory of information applied to quantum systems is really different. I tend to think of entanglement as being wiring without wires, very loosely speaking. There's something that's connecting these 2 qubits, but it's not a real wire. It's not even a physical force. It's the structure of the quantum state that represents those systems. I don't know. Okay. So, so 2 quantum bits, that's not very remarkable either. There's only 4 possibilities, and this state has just 2 of those. But when we add lots of quantum bits together, something really interesting happens. And I think of it as a good news, bad news, good news story when you put lots of qubits together. First, the good news. The good news is every time you add a qubit, you've doubled the space in which the qubits live. So with 3 qubits, there are 8 numbers now, because there are 8 3-bit numbers. And each of these amplitudes follows a Schrodinger equation. And again, they represent the probabilities. They're related to the probabilities of measuring each of those values. And the idea is maybe straightforward here. We have a parallel processor. We can compute things in parallel. And it's not just parallel, it's massively parallel because of this exponential growth. So with just a few hundred qubits, you can store superpositions of numbers, and the number of those configurations is more than the number of particles in the universe. And this is very interesting because there's no way any classical computer could deal with that amount of information, even if every atom in the universe were part of a classical computer. So this is obviously very good news, and maybe as obvious, the very bad news is that you have to look at it. you have to measure the output. And even if you do all this parallel computation, some people would say you can't get the information out. And that's, I think that's a good way to put it, because you have when you evaluate some functions, like a 1-to-1 function, where every input gives a unique output, you have a nasty superposition of outputs. And when you make a measurement, you only get one of them, and it's totally random. And so you don't really have much information. You don't know the input that made this output. So that's not very useful. But the final piece of good news, and this is a little subtle, and it took until the 1990s, I would say, before this came to light. And that is, before you make a measurement in a quantum system, we can guide the Schrodinger wave equation. We can control the system so that there are massive interferences happening. And a good quantum algorithm basically makes interferences happen that are almost all destructive. So the existence of the state 0, 0, 0, 0, for instance, can be made to interfere destructively, except for one or a few answers are remaining. These orange dots are, it's very hard to draw this, of course. It's much more complicated than this, even for 3 qubits. But these red dots, these orange dots, are quantum gates. They allow us to controllably interfere quantum bits. And I'm going to talk a little bit about that in a bit. And the useful quantum algorithm has some number of quantum gates that hopefully is not 2 to the 300. You need to, if it's 2 to the 300, we're back to square one. But there are some algorithms where you don't need too many gates here in order to get an answer that depends on all of the inputs. Okay, so I'm being quite vague here, but this is pretty much how all quantum computations work. They have a massive interference. And then of course you can ask, I'm not going to talk much about error correction, but you can maybe save a question for later. Quantum computers are noisy because they can't be measured in this step here while we're making the interference. And if they're measured, that's called decoherence, information leaks. And so all quantum computers sort of have a limit to how many operations we can perform. And I'm going to talk a little bit about the technology and how we might overcome that. But also there is the idea of quantum error correction that extends very well-known ideas in classical error correction to the quantum domain. Okay, so that's very general. I want to talk about a few general applications and then dive into some hardware, because that's really where the subject I want to arrive at. Now, in the 90s, I think this field really started from Peter Shor, who was a mathematician. He knew a little bit about quantum, but he was mostly a mathematician. And he discovered an algorithm that can be cast in exactly this form. And the algorithm factors numbers. So we all know that factoring for small numbers is easy. Even this number is not too hard on your computer. This number, of course, we memorize in our heads, but factoring is actually an exponentially hard problem. As you add a digit to the number you want to factor, it gets twice as hard. Pretty much every digit you add, it gets twice as hard. So a number with 1,000 digits, we cannot factor those kinds of numbers. And this is why most encryption schemes, most data security schemes rely on the inability to factor big numbers. And there's very simple, the RSA encryption standard is based on that. There's some this is literally just 3 lines of math that shows how you can generate keys, encrypt and decrypt. These are called public key encryption systems. And classically, to break such codes, the time required on a classical computer scales exponentially in the number of bits, little n, that represents the number you're trying to factor. N to the 1/3, that's nice. So every time you add 1 digit, this roughly doubles the time. It's still exponential, even though it's e to the n to the 1/3. Shor's algorithm is not exponential, it's polynomial. It's between n squared and n cubed. And there's a prefactor in front. I don't know what that constant is. I don't think it's very small, actually. But the complexity theory here is that we've changed the structure of factoring to be one of these very hard problems. It's thought that factoring is an NP hard problem, but that's never been proven. But this is the best known algorithm is exponential, and it changes the complexity of the known algorithms for factoring. So this is actually a big deal. There's a real application to these very generic ideas in quantum computing. So here's my embarrassingly silly version of Shor's algorithm. If you want to factor the number 39, well, we take 6 qubits, at least 6, because 2 to the power 6 is 64. So we have enough space to store the number 39. So we store a superposition of all 39 numbers, and we apply gates. I'm not going to tell you exactly what the gates are. There's not too many of them. And the quantum state does this. Through interferences, you can see we get this cancellation of most numbers except for 3 and 13. And then when you measure the system, you get one of the factors. That's basically how Shor's algorithm works. And again, the number of gates you need only scales like roughly n squared or n cubed. Some people would say that's still too hard. N cubed is still a complex algorithm, and that's actually true, but at least it's not exponential. So Shor's algorithm was a big deal. It really put it put the field on the map. The great thing about Shor's algorithm is we can prove things we can show the complexity of the algorithm. And it's an existence proof that there is a useful use case for quantum computers. The problem with factoring is that an interesting number to factor is maybe 1,000 digits. So we're talking 10,000 bits just to store the number. We need some workspace. So let's say 100,000 bits. Remember that n squared or n cubed. If we have 100,000 bits, that's like 10 to the 12 operations. That's 1 trillion operations. And if our quantum computer doesn't have a part per trillion errors, if the gates aren't perfect, we're going to need to do error correction, and the overhead might be, I don't know, factor of 1,000 or something. So now all of a sudden we need 10 million qubits, and we need 10 to the 14 gates. Okay, so that's among the hardest problems we could think of right now, and no hardware is even close to that right now. Now, I can't say we won't get there. I think we eventually will get there, but probably using techniques and physics systems that we don't know right now. But it'll probably happen at some point. So why am I here talking, and why will I talk to you in a few minutes about a company that's actually making these devices? Well, there are many other classes of applications that quantum computers look to be very good for. And these, I think the picture I showed, this one here on the right, tells it all. We're looking for algorithms where there's one answer that depends on lots of inputs. Now, these are problems that are typically not very efficient on classical computers, and I call them optimization problems very generally. So this is a simple example here. In this landscape, the question is, where is the tallest mountain peak? Well, it's right here. You can see it. Actually, depending on the perspective, maybe it's that one, but it's pretty clear where, it's not going to be down here. And the reason this is easy, of course, is that we have a two-dimensional plot, latitude and longitude, and we can just easily map it and see quickly. But if I give you a problem with 10,000 dimensions, that is, say, 10,000 variables, and I give you a nonlinear function and ask for what's the minimum, what are the inputs that give the minimum value of that function? That's a really hard problem. It's a combinatorial optimization problem, and classical computers are horrible at these problems. They're exponential, because you basically have to test every input, and there are exponentially many of them. So optimizations in general are all over the place, and we tend not to do very well in problems like this. Starting on the bottom here, this is a very well-known logistics problem, the traveling salesman problem. What's the minimum path between a discrete number, a fixed number of cities where you pass through every city exactly once? This is a combinatorial optimization problem. Classical computers, there are heuristics that are actually quite good, but we never know if they're the best, what the minimum is. Now, it turns out we all believe that quantum computers also cannot solve this problem. They can't find the absolute minimum, but quantum computers may be able to get a better minimum than what we have classically. So it might be a heuristic. So theorists really hate this, because heuristics, you can't prove anything about them. Experimentalists love, like me, and Marcus and I love this kind of problem, because it means we have to build the systems and just see how well it works. So this is very promising. And of course, traveling salesman is more useful than factoring, I think, because everybody from Amazon to defense departments of major countries need to do this type of a problem, logistics. Now, in physics and chemistry, there's an entire class of problems there. We don't think of them as optimizations, but molecular structure relies on how the electrons situate themselves in a big molecule. This molecule, is this caffeine. This is caffeine. Caffeine has about 100 electrons. Those electrons sort of perform their own optimization by minimizing their free energy. And it's actually a really hard problem to study. Quantum mechanics is doing quantum problems is very hard classically. So a quantum computer might be able to tackle a problem like this, or even much more complex molecules that are very important in light harvesting. This is a molecule that's used for nitrogen fixation to make ammonia from N2. It involves this molybdenum and iron core. And again, this molecule has, I think, 1,000 electrons or something. We really have no idea even how to compute the binding energy of a molecule like that. So quantum computers, I think their first use cases will involve things like things from the physical sciences to begin with. Okay, so with that, sorry, too long of an introduction, I want to introduce the idea of how to build one of these things. And one aspect of quantum computers that really you have to keep in mind, and this is a line I stole from my colleague Bill Phillips at the University of Maryland and NIST, and he's fond of saying that a quantum computer, if that's maybe what it looks like, I don't know, I don't even know what's going on here, but a quantum computer is more different than your laptop then that laptop is different from an abacus. And what he means, what Bill's means here is that a laptop and an abacus are both Turing machines. They can both be modeled by a classical Turing machine. One is a lot faster than the other, of course, but the physics of computing is the same. Whereas here, the fundamental physics of computing is completely different. And I think when we build systems, we should keep that in mind, that a quantum computer probably won't look anything like a laptop. Why should it? And I think we have a natural bias in the world that if a computer, silicon was so powerful, it worked so well in Moore's law that sure, we can build a quantum computer out of silicon. And I think, unfortunately, that's where a lot of the investment has been over the last couple of decades. And so of the technologies to build quantum computers, there's something exotic about all of them. And that is that we have to maintain an extreme level of isolation. When we do our computation, the system has to be so well isolated that no measurement happens, not even by a human set of eyes, but the environment can't interact. Remember the Copenhagen interpretation, we have a black box. Remember Schrodinger's cat's always in a black box. We have to isolate the system. So I would divide the candidate technologies into two classes. One I call synthetic qubits and the other natural qubits. Synthetic qubits are like silicon. They're made typically of solid state systems where there's some level of isolation, maybe because the system usually is at very low temperature. But in the case of superconducting loops, there's also an isolation because the currents in a superconductor flow without loss. So that's in a sense a level of isolation. But all of these technologies, it's very hard to scale them because every qubit, because it's synthetic, every qubit's a little bit different, and those differences can actually fluctuate. And the whole thing has to be at very low temperature. So there's a lot of, I think, fundamental physics that has to be discovered that will allow these things to scale. Now, if you look at the industrial investments in these fields, especially superconductors, there's some big names here. Microsoft over here in silicon, Intel also. I think they're, it sounds bold to say this, but I think these big companies are stuck in Moore's law. I mean, silicon was so great in the classical computing era that I think the people on the synthetic qubit side are blinded. I think they necessarily think that a computer has to be made out of solid state. Of course, I'm here very dramatically to say that the natural qubits, which are by some reasoning even more exotic, individual electrons, photons, atoms, atomic ions, individual molecules. I'm going to talk about atomic ions quite a bit. These systems, we don't manufacture them. We have to sort of produce them and isolate them, but they're sort of given to us. Atomic structure is already there, so they can be perfectly replicated, and I mean perfectly. We make atomic clocks based on atoms for that same reason, because an atom of cesium is the same in Stockholm as it is in Washington, D.C. So it's a standard. And so a standard qubit, such as a single cesium atom, is a good idea. Now, of course, the hard part is how do you isolate a single atom? They're usually part of a solid or part of a surface, on a surface, part of a gas. But there are interesting technologies that isolate individual atoms, and I want to talk about one of them, atomic ions. So here's a picture of exactly 80 atomic ytterbium ions. That's YB isotope 171. They're all the same. They're all the same isotope of the same element. And they're floating above this chip. To give you a sense of scale, this chip is about 1 centimeter across. And in this picture, I've expanded, the atoms are actually right here where the cursor is. They sit about 1/10 of a millimeter above this surface. This looks like a bow tie. Above the bow tie surface, about 100 microns. And the distance from left to right is about 500 microns. So they're this little string of atoms, like a string of pearls sitting there, and we're shining laser light on them, and they're glowing. They're glowing. This is actually near ultraviolet light, and we have a UV sensitive camera. This is all done in a vacuum chamber. So that's one piece of exotic hardware. This has to be done in a vacuum because we can't have nitrogen molecules bouncing against these atoms. So the good news, even at room temperature, this chip is at room temperature, we can hold on to crystals like this for very long periods of time, hours. If you cool down to 4 Kelvin, which is not hard to do, you can make these ions sit there indefinitely, as long as the power is plugged in. And what does the power come in? Well, this bow tie contains lots of electrodes. You can't see, there's about 100 electrodes, and the voltages are applied to suspend these atomic ions above the surface. They're atomic ions, and that's why they repel each other and form this crystal. One thing right away you can see is that the trap, this ion trap, is anisotropic. It's very weak along one axis compared to the other 2 axes, and that's why they form this linear chain. So each atom here is separated by about 5 microns from its neighbor, and you can see the blobs here. Each atom is sort of fuzzed out to about a micron. That's not the atom itself. That's just the diffraction limit of the optics that we use to image. The atoms are laser cooled. Even though the electrodes are at room temperature, the atoms are effectively at millikelvin temperatures through laser cooling. It doesn't require any refrigeration. It's just a single laser, actually. It's a very efficient way to cool a small mass like this. The atoms are about 1,000 times smaller. So each blob is about 10 nanometers or something like that. Okay. So the big picture here is that these atoms, each one of them is a quantum bit, a qubit. I'm going to tell you how we can store qubits in the atoms and entangle them based on other laser beams. Now, because we're shining laser light on them, they're being measured. I'll talk about that a little more, but this is just so you can see the atoms. Of course, when you turn that laser light off, the atoms are still there. And that's when you can perform quantum gates on them. And I want to talk a little bit about that. This chip, by the way, was made by Sandia National Laboratory. They're a Department of Energy laboratory here in the US. They actually have, their main mission is to make radiation hardened silicon. And you can guess why they make that. But they also do wonderful research in fabrication, and they have a small ion trap group that makes these electrodes. Nothing quantum about this chip. It's pretty complicated, but it's just silicon technology, and the electrodes are coated with gold. So this is gold on silicon made at Sandia. There are many different geometries. Marcus knows quite a bit about this. Everybody has their own favorite. It almost doesn't matter. I think my main point here is that what matters, the quantum part, is the atom. All this other is control, and there are many approaches to doing that. Okay, well, let's look inside the atom. Each atom of ytterbium-171 is simpler than you think. Ytterbium-171 plus, it has a single outer electron and a very heavy nucleus, but the nucleus has spin 1/2. And all the other electrons are paired up and sort of frozen out. So it looks a lot like hydrogen. Amazingly, ytterbium-171 plus looks very much like hydrogen. And so there is a hyperfine structure in the S ground state of that outer electron. And 2 of these 4 levels, they're so-called clock states because they have no magnetic field shift to first order. The hyperfine splitting in ytterbium is 12.64281 to 118 gigahertz. This is a pretty good atomic clock. And so that's why we can spell out the frequency splitting. I can give you a few more digits if you want. And for experimentalists out there, if the magnetic field changes by 1 milligauss, this last digit changes by 1, something like that. I think I got that right. Yeah. So the qubit this is what we mean by perfectly replicable. The 2-level system is identical to its neighbor. Furthermore, if we have a single atom in a superposition of these 2 states, they pretty much last forever. The decay from the excited state down here, the lifetime is thousands of years, but even the T2 time, the so-called coherence time, can be made as long as you want. You're typically limited by your measuring device. It reminds me of atomic clockwork. If somebody claims they have the best clock in the world, they can't prove it unless they have a better clock, right? So these are atomic clocks. So to show, even to measure a coherence time, you need a damn good clock to do that. So we're never limited by the idle properties of this qubit. And this is something that's particular to atomic qubits, okay? That's something to remember. These synthetic qubits have T1 and T2 times all over the place. We never talk about that in ion trap work. The detection of the qubit, this is sort of the best part. It's so easy. When we have atoms, we can shine laser light at a particular wavelength so that one state fluoresces and the other state doesn't. It's as simple as that. And we don't have to collect all the fluorescent photons. This is actually data. When a single atom is in the spin up or the one state, this is real data repeated many times. The distribution of how many clicks we got on a photodetector. And I think the efficiency of collecting light was only 1%, something like 1%. So we get a click every microsecond. And when we integrate for about 50 microseconds, we get this number of clicks. If the atom is in the other state, the same laser is really far away from resonance. The excited P state, the first excited electronic state of the atom, just like in hydrogen, it has a line width of a few tens of megahertz, but this laser is 12 gigahertz detuned. So in the other state, the atom is largely transparent. And so we see no fluorescence, almost no fluorescence. There's dark counts, maybe cosmic rays or technical noise down here. But the overlap between these distributions is so small that even in a single shot, we can ask the question, did we get 3 or more clicks, or did we get 0, 1, or 2 clicks? And just by having that binary decision, we can realize very high efficiency qubit detection. And in fact, if you want better than this, there are ways to do that. I think the group in Innsbruck probably has the record with 4 or 5 nines of detection efficiency in a single shot. So this is sort of amazing. We have a coherent system that's nearly perfectly coherent, but then when we want to measure it, we can measure it with near perfection. You rarely get this in physics because measurement is antithetical to coherence, but being able to gate one and then the other is an important thing. Okay. The interaction we rely on most is the one that makes superpositions and allows us to build quantum gates. And this is also a laser interaction. It involves, there are many ways to do this. I'm going to talk about this particular method where we have 2 lasers that are each very far from resonance. Again, terahertz here compared to, remember, the line width was only a megahertz. So we're way outside of the excited state here. But these 2 laser beams have a beat note that exactly matches this hyperfine splitting, and we can get a coherent process going on that allows us to make gates. And if you ask me why we use ytterbium, the reason is a good place to tune the lasers in ytterbium happens to be at this wavelength, 355 nanometers. And this wavelength is a commodity wavelength. This type of a laser, this is a tripled YAG laser. It's an industry standard for lithography of the upper layers of CMOS. And this is a picture of the laser that, again, in atomic physics, we tend to like to tune our lasers, get in the laser frame. This laser, you don't open up, you just turn it on. So this is a big benefit to building a quantum computer, because we don't want to have to play with our lasers for 90% of the time to get the quantum computer working. The laser is pulsed, it produces a frequency comb. I won't talk much about that, but that allows us to generate all the tones we need to do what we want. Okay. So at a very high level, how do we entangle these ions then? And it involves a force. It involves these 2 laser beams applying a force. And we have a geometry so that the one arm and the other arm of this transition are counter-propagating. So there's momentum transfer from the light to the atoms. And that's basically how we generate gates. So at a very high level, and these ideas were first codified right after Ignacio Serac and Peter Zoller learned of the Shor algorithm. They said, wait, with trapped ions, we can make these gates. And it was later refined by Molmer and Sorensen and others in the late 1990s. The basic idea is this. If we have these atoms in a string and we want to do a gate, it turns out all we need to do is a 2-qubit entangling gate. And if we can do that on any pair, we can realize an arbitrary quantum computation. And the basic physics is that if we want to entangle, say, this ion and this ion, we apply 2 beams. And in this case, there are many ways to do this. This is just an example. These 2 beams come from the side and they apply a force to the atom, but the force depends on the qubit state. That's the key. That's the quantum part. The force itself is classical. It's called an optical dipole force. If you've heard of the term optical tweezers, it's pretty much what's going on here. But we can tune the lasers so that the direction of the force depends on the internal state due to selection rules and tunings and so forth. So the simplest picture is to imagine that if we have two atoms in the state 1, they both move up, or state spin up, they move up. That's easy to remember. If they're in the state spin down, they both move down. And if that's the case, their Coulomb interaction, just these two atoms, forget the other ones for a minute, these two atoms have the same Coulomb interaction as they had before, so nothing happens. But if they're in the odd parity states, 1, 0 or 0, 1, then they're tilted. They're a little further apart, tiny bit further apart. And the displacement of this force is a few nanometers, really, it's small. But if you look at the difference in Coulomb energy between the tilted configuration and the straight configuration, we actually have a sizable interaction energy, and it actually falls off like 1 over r cubed in this case, because we're sort of making an electric dipole here, and we have a dipole-dipole interaction. It will fall off like 1 over r cubed. It's a very strong dipole. We're engineering a dipole by moving the atom. Now, I'm looking at Marcus here. He is a pioneer in a different way to make this dipole by actually, it has advantages. You can make the dipole within the atom itself by promoting the electron to a very highly excited state. And the advantage there is that it's less floppy. You're not moving the entire atom around, so it's a lot faster, that type of a gate. But the essential physics is very similar. And also what people do in neutral atoms is very similar by exciting the electron. So what happens if you look at the four possible states of those 2 qubits, as I said, nothing happens to down, down, or up, up, but the 2 odd parity states, they suffer this phase factor because of that energy defect. And it's the same, whether you're up, down, or down, up, because it goes like delta squared, it's the same phase factor. This gate is nonlinear. This is actually a universal gate right here. It doesn't look like it entangles, but it does in a different basis. I won't get into that. But when we set the phase factor to pi over 2, we have something that is sort of like the AND gate. It's sort of like, we call it a controlled NOT gate. And that is universal for computation. So the picture now is then we shine laser beams hitting any pair of ions, and that allows us to do a gate. Now, to flip a single bit and make a superposition, that's really easy. I didn't even talk about it. We use a single laser, no force involved. It's like nuclear magnetic resonance. It just flips the hyperfine level. So in practice, we actually do this in the X basis of the spins. That's kind of technical, but we end up with an evolution operator that's an Ising interaction. This is our native interaction with trapped ions. It's an Ising gate. The fidelities can be very high. The state of the art, even in long chains, is about 99.9. It's not good enough to do 1 million operations. We need to improve that, but it's good enough to do about 1,000 operations. And the gate time is actually fairly slow. One thing I didn't point out is that when we pluck these 2 atoms, there are normal modes of vibration. These are typically megahertz, which means their period is about a microsecond, but this gate is much slower than that. And so that means when we pluck these 2 atoms, they all move. It's actually a complicated mess, but it's a classical complicated mess that doesn't scale too badly with size. It's not an exponential problem. In practice, we laser pulse shape. We don't just pluck the 2 parts of this string. We push on them in a very prescribed way so that all of the motion cancels at the end and we're left with this entanglement. I know again, I only have limited time to talk about that. The great advantage of that is that we don't have a dipole interaction anymore. It's full on. It's all to all connected. Every pair has its own laser pulse sequence, and the gate speed is the same no matter how far you are apart. And it's because normal modes are delocalized. I mean, if you look at the tilt normal mode, the ions that are furthest apart have the biggest contributions to that mode. So because the Coulomb interaction is so strong, we get an all-to-all connected system. And there are many, many variations on this type of a scheme. And I pointed out, using Rydberg excitations within an atom. That's a very interesting variation. There's another one, actually, this is very recent from one of my postdoc, or Katz. he showed us how by using spin-dependent squeezing operations in addition to these displacements. So when you literally squeeze, that's sort of an interesting quantum interaction. We can get n-body interactions, so full n-body, not just pairwise icing interactions. So this is, again, a theoretical result, and we're looking forward to implementing this. So this next is a little cartoon of a quantum circuit and how it might look in a trapped ion quantum computer. So here we have a space-time diagram. Space is vertically, we have 7 qubits, and time goes from left to right. These are a bunch of gates, and here's how an ion trap quantum computer works. We first initialize all the qubits in a particular state using optical pumping. I didn't talk about that too much. And now to run the gates, you can see when we have multi-qubit gates, the ions are actually moving, making those little dipoles if you want. And all these lasers are pulse shaped, and depending on the algorithm, we need to control which laser beams are on and off and so forth. And then after the gates, we make a measurement by shining a laser beam that gives you state-dependent fluorescence. And so those atoms that are bright are ones, those that are dark are zeros. Okay, as simple as that. It's easy to make a PowerPoint ion trap quantum computer, but when you look in the lab, and this is probably why I gave a hard time to the big companies investing in silicon. I think maybe they did this because they looked at our labs, and if you look at Marcus's lab, you'll see the same thing. You know, it's just a bunch of wires, a bunch of mirrors, a bunch of lasers. It's kind of a mess. And when you're conducting research, we want to have all this flexibility. We want to be able to tune every oscillator to any frequency. Every mirror has enough screws to do everything we want. But if we know what we're going to build, we can freeze in a lot of this design. And when you have an optical system that you're shrinking and making frozen, it can get very small. And without much exaggeration, everything you see, by the way, you can't even see the vacuum chamber here is very small compared to the whole table. But we're now at the level where the vacuum chamber is the biggest part of the system. Most of what you saw on that last slide in our latest system was packed inside this box. It's a couple of meters cubed. It was made in a big collaboration between Duke and University of Maryland, where I used to work, funded by IARPA and the NSF STACK program. And I mentioned Sandia make the chip, and these other companies, they help us on the optical integration. They make optical devices for us that can make this work. So when this box is closed, we leave it closed for many months at a time, and any adjustments we need to make can be done remotely and electronically. So this system does behave a lot better, and it looks a little more like a computer, even though it's still kind of big. But when you look inside, you'll recognize what all these pieces are. We basically have counterpropagating beams. I mentioned that, right, to apply these forces. One of those counterpropagating beams is split up into 32 individual beams that each of them has their own modulator, and each of these 32 modulators has an RF input. So it becomes a control problem of RF. So we have very fancy FPGA controllers and so forth to do that. But it's actually schematically fairly simple inside there. And what we realized in building this early system is that while there's a lot of atomic physics that goes into laser cooling, controlling, loading these atoms and the ion traps, we spent more of our time up here in the quantum computer stack. I talked about pulse shaping. We have to calculate these laser pulses, these classical laser pulses that do what we want, and that gives us icing gates. But textbooks have controlled NOT gates, and they're not the same thing. So translating from one to the other takes some work, and we can compress. This is what I might call the quantum compiler. It sounds more like a software tool. And then at the very high level, we have an application like Shor's factoring algorithm. So we found ourselves in the morning tuning things up, and then in the afternoons running algorithms. So this is more like what a user wants to do in a computer. And so we started thinking about what we can do with this. And in fact, many colleagues would ask us to run certain applications. Some of them were not general purpose, but more quantum simulators. But what's been very fun in all these collaborations is that these people are coming from all over the place, even some companies, and they're running applications on, say, the IBM cloud system, and it generates noise. and we don't have a cloud system, or we didn't back then. And so this would be a few years, sometimes, research project where we would run circuits and iterate and make the circuit more compressed, attack noise, design our gates to be tailored to a particular application. So that was a different kind of research. And the last couple of years have been really busy as our systems get more and more mature. And I should acknowledge Norbert Linke, Marco Cetina, and Crystal Knoll, all who are now on the Duke faculty in our Duke Quantum Center. They were quite responsible for making these collaborations and making everything happen. So I want to give you just a few examples of some of these projects. One comes from condensed matter, and this is to measure. This is more of a quantum simulation than a quantum computation, because we're implementing a global Hamiltonian. It's not gate-wise, but it's all at once. We turn an Ising coupling on all pairs, and this is a long-range Ising interaction between ions I and J that falls off with some adjustable inverse polynomial here. And then we have a transverse magnetic field. It's transverse because the Pauli spin operator is Z here compared to our native X Ising gates. And so this is an interesting Hamiltonian because there's a phase transition to be expected here, depending on the relative size of B and J. If B is really big, then you can say that atoms would be polarized along the Z field here. But if J is really big, they will order according to the structure of J and this XX interaction here. Now, what's interesting is that there's, even if you're not in the ground state, the equilibrium, you can be in an infinite temperature state, and there's still something akin to a phase transition, which I found kind of interesting. Sometimes it's called a dynamical phase transition. And so in this experiment, it's actually a very simple one. We prepare all the spins along the X direction of the Bloch sphere, that's up plus down. And then we turn on this Hamiltonian for particular values of J and B, and then we measure along X. So these are measurements of the magnetization, which is simply the brightness. I love this observable. You just look at the collected light, and that's proportional to the magnetization. And you can see for high B over J, relatively high B over J, indeed, this term dominates, and the spins precess around the Z-axis. I guess this way. They precess around the Z-axis, and we see, when we measure along X, we can see that precession. Of course, it dies away because there's lots of inhomogeneities and so forth. But you see quite different dynamics when B over J is much smaller. You do see some sign of the wiggles, but there's not much going on. It's because the spins are already along X, and nothing really exciting happens. They're already along X. They're already near an eigenstate of H, so nothing happens. And of course, in between, I wouldn't call this a phase transition, but there's definitely different dynamics. Well, the magnetization is kind of boring. Let's look at the correlation between spins. Here we're plotting versus different numbers of spins, the two-body correlator as a function of B over J. And what we see is that at intermediate values of B over J, there's sort of a minimum in this correlator. And as the number of spins grows, this minimum gets a little more pronounced. Now, the dashed line is mean field theory. You can see it sort of, you can do mean field theory here, but at the end, it doesn't work very well. And the solid line is an exact diagonalization. With a few spins, you can do this. With 53 spins, we couldn't do the exact theory. 2 to the 53 was just too big for our computers. So this dashed line is just a guide to the eye. Again, I wouldn't call this a phase transition. It's probably not sharp enough. In the infinite limit, it should be a logarithmic divergence. But of course, that doesn't look like a divergence to me. It's just a dip. So we measured, remember with these ions, we can measure any correlation function. So in this case, we measured a very strange order parameter, and that is, in every shot, what's the size of the largest domain? All up or all down? And in these pictures, as we increase B over J, we take an average of, we take a bunch of shots and we plot the average largest domain. And this, it's not clear, you have to really think about it, what's going to go on here, but it turns out that this is much sharper than it's because it's an n-body correlator in general. And the take-home message is we couldn't calculate, this is actually at 0.97, I think. We couldn't calculate where that minimum should be. And these lines are just fits to, having two linear fits. This was a collaboration with Alexei Gorshkov at JQI, but we're doing many spin type experiments like this with others, including many beta-localization experiments, David Hughes, Sonic Ajori, and Norman Yao, and many others. So this is one class of experiments, I think, with these trapped ion simulators, we're able to hit the spin chain equilibrium and dynamical processes. And these get really hard to calculate, even 53 spins, it's very hard to calculate. I'm running a little low on time, but I wanted to cover one more application that actually hits cosmology, strangely enough, and that is the concept of quantum scrambling. So scrambling is more than entanglement. It's, in a sense, entanglement at all depths. And so you need at least 3 qubits for a unitary to scramble, where the scrambling is more than just entanglement. And this circuit, I don't have time to go into details. This circuit tells you whether the unitary operation here expressed in terms of gates, whether it scrambles or not. And you have to implement U and its inverse. With gates, that's not hard to do. Basically, the physics of this gate, this 7-qubit circuit, is that if you have an arbitrary input qubit here, if U scrambles, then this qubit will appear on the 7th rail. It actually gets teleported to the 7th rail. That's a technical term, believe it or not, teleportation. Kind of unfortunate, but anyway, the quantum state appears there. And so we can just measure that state and see whether U scrambles or not. And U is supposed to be a black hole, because the connection to black holes is that that when you put a qubit into a black hole, it's thought to scramble with all degrees of freedom of the black hole. And this is based on some pretty high power theory, Lenny Susskind and others that kind of showed us this way. For U, we implemented a very generic 3-body circuit where we have a parameter that we can tune the amount of known scrambling in the system. And this is sort of, the problem with a few qubits is that you always know what you're going to get. It's small enough, you can calculate it. But this is real data showing the teleportation fidelity. 0.5 is the classical limit. And as we increase theta to 90 degrees, as expected, we expect there to be scrambling present in U, and it is detected there. And so, to me, what's amazing about this field, and I'm still, a student, I'm not sure I even believe it all, that there could be a deep connection between entanglement and teleporting through a wormhole. This is, these are real words that cosmologists use. There's a connection between these Einstein-Rosen bridges and the Einstein-Podolsky-Rosen, entanglement paradox. So the reason I like this example is that it's very far removed from atomic physics or even quantum information. So I think the use of quantum computers, this is an example of that. It's going to be applied to science. It's going to be applied to all branches of science. And that to me is very exciting. I'm really running out of time. I'm going to skip that. I will say though, that this experiment required us to measure a subset of the qubits while not affecting the other. And so for this, with trapped ions, we actually physically, in the middle of the circuit, we split the chain and then measured 1/2 of the chain. And then we brought them back together and did operations. Now, I wanted to spend a few minutes talking about IonQ, because this does look like an industrial, to get to the next level of performance, we're going to need an industrial engineering approach. And this is why Jungsang Kim and I started the company IonQ about 5 years ago. And things have moved just incredibly fast. We've built 6 generations of quantum computers. A few of them are on the cloud that you can get from Microsoft or Amazon or GCP, Google Cloud Platform. And we have another 3 on the way, and we're designing 3 after that right now. So the big news in the last few years at IonQ is that I still kind of shake my head when I think about this. IonQ is a public company now. We've had investors that are sort of agreeing with our roadmap plan. And last October, we actually rang the bell at the New York Stock Exchange. It was quite a spectacle, I must say. But what this gives us is a big war chest of almost $1 billion in the bank to prosecute this plan, to go after it and build ion-trap quantum computer systems that can be used for commercial activities. To give you an idea of what IonQ can do, that it's very hard at a university, this is a Sandia trap, one of our earlier generations. And what we're doing here is we load ions one at a time from a little hole here, you can't see it, and each atom is shuttled between all these electrodes over to the zone where we're doing our computation. And we asked this system to load 24 qubits, exactly 24. And the camera is monitoring how many there are. You can even see they're zigzagged here, because the trap is optimized to load a big chain. And now we have 24 dots. We expand it to make them linear, and then we refocus the optics. Now we're ready to go. Now we can run gates for the next several hours until we need to load this again. And that picture was real time. And that amount of control, the ability to do that, is something that I think we could do at a university. It's just very hard. The stability. I mentioned these systems. Some of the earlier systems are on the cloud, so you can actually run circuits right now if you have an Azure or AWS account or a GCP account. And more than just being kind of a publicity stunt, putting small, I would say useless quantum computers on the cloud, people are starting to use our systems and understanding the expression of gates, the Ising gate as their native gate, and wiring circuits in a certain way. They're compiling, they're running small routines, getting used to this system. But more than that, I think it was a great exercise for us to do, because it made us engineer our system so that it works around the clock. Well, at least 80% of the time. So these systems, when we first started, we were calibrating a lot. We were having to load a lot. There was downtime, but we've engineered the system enough now that it's about 80% up. We do a lot of calibrations. These laser pulses have to be calibrated as things drift slowly. And just learning how to automate something is very important in the long run. Again, I'm gonna skip through some of these, except I want to point out this is very recent. What we like to do in quantum computing is add more qubits and have higher quality per qubit, more gates. That might seem like a very hard thing to do. It is very hard, but I think with trapped ions, it's not impossible to think about scaling up to 100 qubits and 10,000 operations. And in general, we want the number of qubits the number of gates to be roughly the square of the number of qubits. This is not always true, but Shor's algorithm was n squared or maybe n cubed, but different algorithms have different complexities. And by running many different algorithms, this is the number of qubits, the vertical axis, and this is the number of gates we're running. Both, let's see, this is a log plot on the x-axis here. And the color code, blue is good, red is bad. The probability of success of these algorithms. I didn't define many of these algorithms, but they have a yes/no answer. Many of them do. I guess Shor's algorithm could be on here. We didn't run those, but we're running on different systems. This is actually, we're running on IonQ, but these other systems were run by the Quantum Economic Development Consortium. They're trying to benchmark quantum computers. And basically the squares in purple are the minimum, they basically tell you how many qubits you can run n squared operations before the answer starts to dip below 50%. And so the performance of our systems by this measure is quite good. And we call this algorithmic qubit, the number of qubits we can have that supports n squared operations. And again, I'm sorry, I'm going so fast, but at IonQ, we do have a very aggressive roadmap that will build up the algorithmic qubits to break through 60 to 100. And when we're in this regime, we can't simulate anything going on here on a classical machine. Now, you might say, well, what are we doing now? We're not moving very fast. But remember, algorithmic qubits, every time you add an algorithmic qubit, you've doubled the strength of the system. So we're going to invoke error correction in 2024 to be able to increase the error, to decrease the errors even more. And then we have ideas on modular scaling. And again, I'm so far down on time, I just don't have time to talk about it. In addition to shuttling ions from zone to zone, we don't want to put too many ions in one crystal. This is real data in 4 times 16 separate linear chains at IonQ. We've been able to bring them together and separate them. We haven't yet done any operation gates on this. This is just showing the control of the ions. And then in the long run, again, I'll skip by that one. In the long run, there are protocols for optically interconnecting chips, going off chip using an optical switch. And again, sorry, I went so fast through this. This is the IonQ part, but this is really the out game at IonQ. We want to be able to stamp out modules and wire them together photonically. And as part of that scaling strategy, our systems are indeed getting smaller over time. Right now, we're packing a vacuum chamber that's on the chip itself. So this is the entirety of the vacuum chamber. There's a tiny ion pump not shown. It's really small, but they're optical access from Windows. We look forward to eventually integrating on chip. We're not doing that now, but this is a picture from MIT Lincoln Labs. And then again, the photonic interconnects in the long run are really where we want to go. And almost last slide here. This is another picture of the number of bits and the number of qubits and the number of ops. And we need to be in this orange region to do something that we can't simulate classically. And we're sort of on the verge of that right now. And you'll note up here, the factoring algorithm is really far away. So, but I think many feel that there will be some algorithms that come up as soon as we build the machines and just see how well they operate. And as a final appeal to the scientific use of these machines and the university approach to building novel quantum computers, is that this is from a business book. You may have seen something called the hype cycle of a new technology. Everybody gets excited, and then it turns out it's harder than you thought. I think silicon went through this in the 50s. People got disillusioned. Now, the good news is there's a long-term upward slope. You know, it's viable. But if people get too disillusioned, then the investment goes away. And people are really worried about this in quantum. I think that the scientific use cases are the ones that will pay the bills over the next few years and keep the momentum going so that industry will eventually find a commercial use case. And, you know, like the cosmology, I mean, no company's going to pay to understand a black hole or, you know, studying condensed matter phase transitions, as I mentioned. So these scientific use cases are very important. It's why universities have to start using these machines, building them, building, you know, like Marcus, I keep mentioning his experiments because they're beautiful. It's a novel way to think about scaling in a different axis. His gates will be a lot faster, and they may allow many opportunities. So what we're doing at Duke, this is my last slide, at the Duke Quantum Center is building systems. As you've seen, that big black box is in this building here at Duke. And we're making a user facility where people can come in and help us design the next generation for their type of a problem. It could be quantum chromodynamics, you know, lattice gauge theory. It could be understanding a biologically hard computation problem, like DNA splicing and so forth. There's lots of computation behind that. And so we have groups from physics, electrical engineering, chemistry, the life sciences, mathematics, and computer science to do this. And I think all universities having a quantum center should really think about this mode of going forward. And eventually we know industry is going to sort of pass us on the technology, but that's great. That means that we'll be able to use their things for science and help them develop the next generation devices. That's what happened with silicon. Thanks for your attention.
Thank you very much, Chris, for this really, really enlightening talk. So are there questions? So maybe one first question from my side. So from a physicist point of view, of course, getting to lower error rates and to lower better performance of these quantum computers is probably more of a technological development than really a physics problem, or what? How do you see that now at the moment?
Yeah,
it's actually interesting for a physicist to do in that area.
Well, you know, I don't know. We've seen this. If you look at accelerators, if you go to CERN, I mean, look at the Atlas detector. I mean, the amount of engineering going into that is insane. And at the end of the day, you can study muons or something. You know, there's some physics at the end of the day. That's exactly what's happening in quantum computing. We do have to go through this engineering phase. We have to build reliable systems, bring the error rates down. But what we're doing is allowing us to study many-body physics, to study complex entanglement. And that's a totally open book. As I said, I think the first thing I said is we don't know exactly, you know, what the use cases will be for quantum computers in 20 years. There's almost no sector of science or even the economy that is free from potentials in quantum computing. So indeed, there's a lot of engineering involved. And in fact, I'm now, for the first time in my life, my main appointment is in electrical engineering and electrical computer engineering. I have a joint appointment in physics as well, because physics owns this field. So physics will always own this field, but I think we do need to branch out. This field is much bigger than physics.
You compared in the beginning of the talk, you talked about classical computers and their development and compared to the quantum computers. And or at least maybe it's with historical hindsight or something, the evolution of a classical computer seems rather linear. So we had one technology, we found a better one, and then a better one, and then we can sort of finally silicon, where we have been now for a long time. The development of quantum computers seemed to more fan out into various parallel tracks of hardware. What does that say anything about the future, or is that a positive thing or a negative thing? Can we draw any conclusions from these two differences? Thanks.
That's a really good question. I'm myself, I'm learning. I didn't know much about classical computing history until the last 10 years or something, and it's fascinating to read about it. And we have to be knowledgeable of what happened back then, just to maybe avoid pitfalls, or I don't know, maybe we're destined to follow the same path of history. I think right now it is sort of like the late 40s or early 50s, where vacuum tubes were still there, and semiconductor physics wasn't quite at the level where we could get an integrated circuit. I think the integrated circuit really came about in the late 50s, I believe. I'm forgetting my history there. So I'm not sure what to say. I think I'm a little disappointed, in a sense, over the last 20 years that we only have, if I showed that first slide 20 years ago, it would have been completely valid. That we haven't expanded the potential qubit technologies much over the last 20 years. That's true. There's this idea of a topological system typically in a solid state where you get natural error correction. It's beautiful. It's a matter of physics, really. It's profound, but there's no overriding evidence of it. There may be a hint of it here and there. There's some recent news on that. So I'm not sure how to answer the question. I think the one nice thing about trapped ion systems is that we are not thinking so much about the atomic system anymore. We're thinking higher level. And I think even if the ground floor changes for us and it goes to neutral atoms or single electrons, having the higher levels of the stack will be very useful. And it's like silicon. If we switch from silicon to gallium arsenide, I think a lot of the understanding of computer architecture on top of that would still be valid. The one counterexample I'll make of that is photons. I think optical photons, I would make a bet that they're going to be here forever in quantum computers, because because there's optical interconnection technology. Photons can go through even glass without being disturbed. In some cases, through free space without being measured. So the hard part is interfacing them with a memory, of course. But I think optically active qubits, and of course trapped ions have that, atoms have that. That's probably going to be here. But this is like saying electrical current will be used in regular computers. Of course it will be. I guess maybe nobody questioned that. I think the photons are sort of like the electrical currents in the 50s. But I think you're right. The memory, right now I think trapped ions are in the lead, but that may not be. That probably won't be true in the long run. So we have to keep that in mind. I don't even think I answered your question, but it's very interesting to compare the histories.
If you were now to say, how do you see it in a long term, the trapped ion systems now, concerning scaling that to a large number of qubits, concerning getting the best fidelities, getting quantum error correction to run, and so on? I think these are all steps that need to be taken to really make it a system that can be commercially really useful for quantum computation and for quantum simulations. Is there any roadblock that you foresee, or is it just money to develop it? Or
I don't know. I see lots of big challenges ahead, but I don't think any of them are fundamental. Let me put it that way. I mean, all right, in the system I talked about, the clock speed is very slow. It's, nobody would buy a modern computer with a 100 kilohertz CPU clock. Of course, a quantum computer with 100 kilohertz is okay because you have this inherent entanglement scaling and so forth. But if it takes a solid year to run some algorithm, You know, if you need to just do the math, if you're running at 100 kilohertz, but you need 10 to the 12 gates, you know, that's 10 to the 8 seconds. That's a couple of years. What we've learned already is that there's a lot of developments up in the software part of the stack that can condense the number of gates you need to begin with. But that's a little bit of a sidestep. I think you know, the clock speed issue is not really fundamental. I think we can also get faster gates, you know, following your technology, or much higher laser powers, things like this. I don't want to paint too rosy a picture. I mean, I do think that the trapped ion, the unique advantage of trapped ions is that everything we're going to do going ahead has been demonstrated in a laboratory environment at small scale. So the physics is sort of done. That might sound disappointing, since most of you are physicists.
Not for us anymore.
Yeah. I know I come across that a lot. But you know, that's not exactly true. I think there will be a shifting of the ground floor based on atomic physics. But I think the counterexample are these solid state technologies. I think there's wonderful physics to be done there, but it's fundamental breakthroughs they need to scale. I don't think anybody knows how to scale a superconducting system beyond you know, 20 or 30 usable qubits. That's a really strong statement, but the performance is not getting better in these systems as they make them bigger. But with trapped ions, we have the history of atomic clockwork behind it. We know that we can get to maybe 4 nines, 99.99% native fidelity. And beyond that, we're going to need to do some error correction, but the error correction is easier if you're better from the starting gun. If you have low errors, the error correction overhead is not so bad. So to get 5 or 6 nines of fidelity requires some serious error correction. We need a lot of qubits. So we need a qubit factory. And there's a whole lot of engineering on how you shuttle the ions around, how you integrate optics. And these are technologies I don't know much about. We're going to have to invent them along the way. And you know, I was deliberate in making the comparison to silicon. Silicon in 1950, I mean, was nothing. And now look what we have. We learned that we had to make a clean room, and to grow silicon in a certain way, there were certain technologies we had to invent. I wouldn't say they were really physics. Maybe you could argue maybe they were, but we just made things better. And I think optics is really the path forward on all of this. We have optical controllers and optical conduits in the long run. So I think we do need, returning to the earlier question, we need a healthy dose of optical engineering in these systems. So I'm pretty bullish. I think using these systems in the future will find the use case, and it might not be the ones we know now.
Okay, then there's currently no further question. Then I think I'll close this colloquium. Thank you very much, Chris, for a really excellent talk.
That was my great pleasure. Thank you, Marcus. Nice to see you again, and I look forward to visiting.
Thank you very much, and thank you everyone for attending the colloquium, and have a nice evening. To you, Chris, of course, have a nice afternoon.